That little padlock. You've seen it thousands of times. You've told users to look for it. You've set up HTTPS on your own apps. You've seen the red error pages, clicked proceed anyway on localhost, and moved on. But how does this work? Most of us picture it something like this. Your browser gets the server's key, encrypts the data with it, and the server decrypts it on the other end. That's not what happens. What actually happens is different. We'll go through how TLS works, what's inside a certificate, what a certificate authority does, and how to debug common certificate errors. Before we get into the details, we need to be precise about what TLS is defending against, as it's not just encryption, that's only one of three problems. When you send an HTTP request, it doesn't go directly from your laptop to the server. It hops through your router, your ISP, multiple backbone routers, and eventually arrives. And you don't own or control most of this infrastructure. Any node or anyone sitting on the network between them could, in theory, read or change what you're sending. TLS solves three distinct problems at once. Confidentiality. Can someone read the data in transit? Integrity. Can someone modify the data without you noticing? Encrypting your bank transfer amount doesn't help if someone could change it after you sent it but before it arrived, and you'd have no way of detecting that. Authentication. Is the server you're talking to actually who it claims to be? If I could get your browser to connect to my server instead of your bank's, even with perfect encryption, you'd be securely handing your credentials to me. The connection would look completely fine from your end. Encryption without authentication isn't security. It's just privacy for the wrong party. Keep all three in mind. Everything in TLS maps back to one of them. TLS uses two fundamentally different types of encryption for different reasons. In symmetric encryption, both sides use the same key. One encrypts, the other decrypts. AES is the most common symmetric cipher today. It's fast. Modern CPUs have dedicated hardware instructions specifically for AES. This is what actually encrypts your session data. The problem is obvious. Both sides need to have the same key. And if they've never communicated before, how do they get it? You can't send it over the wire. That's the wire you're trying to secure. Any channel you use to send the key is a channel someone could be watching. You've probably felt a version of this, that moment when you need to share a production database password with a teammate and someone suggests Slack, and you know it's wrong, but you do it anyway. That instinct is correct. If anyone's watching that Slack channel, the secret's out. Before public key cryptography, the solution was to exchange keys in person or through a trusted courier. Fine for closed systems. Completely impossible at the scale of a browser connecting to any website it's never visited. Public key cryptography, developed in the 1970s, solved that. In asymmetric encryption, you generate a key pair, a public key and a private key, mathematically linked, but you cannot derive one from the other. The core property, what one key encrypts, only the other can decrypt. This means you can make your public key completely public, post it anywhere. Anyone can use it to encrypt a message to you. But only you, with your private key, can decrypt it. The main asymmetric algorithms in use, RSA and the elliptic curve variants, are orders of magnitude slower than symmetric encryption for bulk data. You cannot use them to encrypt an entire session's worth of streaming traffic. So TLS uses both. Asymmetric to securely establish a shared secret between two parties who've never met, then symmetric encryption with that secret for everything else. That's the architecture. Let's see what it looks like in practice. When you type HTTPS bank.com and hit enter, before a single byte of your request goes out, a TLS handshake runs. Your browser sends a client hello, announcing what it supports. This includes the TLS version. You know that browser warning about outdated security protocols on old corporate intranets? That's cipher negotiation failing. The client and server couldn't agree on a shared modern cipher, so they fell back to something weak or gave up entirely. The client hello includes a list of cipher suites, each one specifying a symmetric cipher and hash the client can use. Think of it as the browser saying, here are the tools I speak. The server picks the one it prefers from that list. The client hello also includes a freshly generated client random, a value that'll matter in a few steps, and a key share, the client's first move in the upcoming key exchange, sent proactively in TLS 1.3 to skip a round trip. The server responds, picks a cipher suite, sends its own server random and key share, and sends its certificate. The certificate is the server's proof of identity. It contains the server's public key and a signature from a trusted third party. The browser has to decide whether to trust it. We'll answer that soon. For now, assume it checks out. How do two parties agree on a shared secret over a completely public channel without the secret ever appearing on the wire? TLS 1.3 uses elliptic curve Diffie-Hellman ephemeral, ECDHE. The concept of establishing a shared secret without transmitting it was published by Diffie and Hellman in an open paper in 1976. ECDHE is the modern elliptic curve variant of that idea developed in the 1980s, faster and more efficient. But the counterintuitive property applies to both. The entire method is public knowledge. An attacker can read every paper about how it works, understand every step, and still cannot break it. Security doesn't come from keeping the method secret. It comes from a mathematical property that makes reversing the operation computationally infeasible. Worth sitting with that for a second. Both you and the server start with a shared public color, say yellow. Anyone watching can see it. You pick a private color, dark red, that only you know. You mix it with yellow and send the result, orange, to the server. Your dark red never leaves. The server picks its own private color, dark blue, mixes with yellow, sends you green. You take what the server sent and mix in your dark red. The server takes what you sent and mixes in its dark blue. You both land on the same final color. Neither of you ever transmitted your private color. The eavesdropper saw yellow, orange, green, and cannot reverse the mixing. The math makes it infeasible. That's Diffie-Hellman. Both sides now hold a shared secret without it ever crossing the wire. One more thing, the word ephemeral. ECDHE generates a completely fresh key pair for every single session. This gives TLS 1.3 a property called forward secrecy. So, if a server's private key gets stolen years from now, an attacker who recorded your traffic today gets nothing. The session keys existed in memory for the duration of the handshake. They're gone. Without forward secrecy, a leaked key could unlock all previously recorded sessions. ECDHE closes that window permanently. From the shared secret, combined with the client random and server random from the hello messages, both sides independently run the same calculation through a key derivation function. TLS 1.3 uses HKDF. Both sides derive identical session keys because they had identical inputs. The randoms are what make every session cryptographically unique. Without them, two connections to the same server using the same DH parameters could theoretically produce the same session keys. If an attacker ever obtained those keys for one session, they might apply them to another. The randoms eliminate that possibility. Every session's keys are unique, even if everything else about the handshake is identical. Separate keys for direction, separate keys for message authentication. Conservative by design. The server sends a finished message encrypted with the newly derived key. The client verifies it, confirming derivation worked on both sides, then sends its own. And now your actual HTTP request goes through. Fast symmetric encryption doing the heavy lifting. All of the asymmetric math was purely to get here.
The whole handshake in TLS 1.3 one round trip. TLS 1.2 needed 2. That difference is measurable in real page load times, especially on mobile and high latency connections. We skipped a step earlier. The browser got a certificate. How does it decide to trust it? This is authentication. The difference between the connection is encrypted and the connection is encrypted to the right server. A certificate authority, a CA, is an organization that browsers and OSs have agreed to trust. When you want a certificate for your domain, you prove to the CA that you control it by placing a file at a known URL or by creating a DNS record. The CA verifies that, then issues a signed certificate. The CA signs your certificate with their private key. Your browser verifies that signature using the CA's public key, pre-installed in your browser OS when it was shipped. So when your browser gets a certificate for bank.com, was it signed by a CA I trust? Can I verify that signature? If yes, the certificate is legitimate and hasn't been tampered with. Nobody can fabricate a valid signature without the CA's private key. The CA is the trusted third party saying, "We checked, the entity requesting the certificate genuinely controls bank.com." In practice, CAs don't sign your certificate directly from their root. They use a layered structure. Your server certificate is signed by an intermediate CA. That intermediate certificate is signed by the root CA. The root's public key is pre-embedded in your browser and OS. When your browser validates a certificate, it walks that chain, verifying each signature until it hits a root it knows. This is the chain of trust. Break any link, expired cert, missing intermediate, revoked, and the browser rejects the whole chain. Root CA private keys live on dedicated hardware called hardware security modules, HSMs, in physically secured facilities, often requiring multiple authorized people to operate. Most root CAs keep this hardware completely offline. If a root CA's key were compromised, browser vendors would need to push emergency updates to distrust that root across every browser and OS worldwide. Every certificate it ever signed would need to be reevaluated. So, root CAs sign a set of intermediate certificates, then go offline. Intermediates handle day-to-day issuance. If an intermediate is compromised, revoked, certs invalidated, the root is untouched. The blast radius stays contained.
Identity, validity, signatures, chains, it's readable as plain text inside every certificate. One command. Certificates follow a format called X509. Field by field, here's what you're looking at. Subject, who this certificate is for. CN equals *.google.com, the common name. That asterisk is a wildcard. One level only. Mail.google.com, yes. Anything deeper, no. Issuer, who signed it. Google's own intermediate CA. This is the link in the chain directly above the server cert. Validity, a hard window. Past the not after date, the certificate is dead to browsers. This is the field responsible for most midnight emergency pages. Subject alternative names, SANs. This is the field browsers actually use for domain validation, not the common name, the SANs. The CN is a legacy field. If you've seen certificate verify failed in your stack trace and had no idea which field was wrong, this is the first one to check. Those four are the ones that break things in production. The last three are why you can't fake a certificate. Public key, the server's actual public key, embedded in the certificate. In TLS 1.3, the server signs its key exchange data with the corresponding private key. Your browser uses this public key to verify that signature, confirming the handshake came from the server that actually owns this certificate, not an imposter. Signature, the CA's cryptographic signature over everything above. Change anything, the domain, the expiry, the key, a single byte, and this breaks. You cannot forge it without the CA's private key. Key usage, what this certificate is allowed to do. A web server certificate cannot sign other certificates. Even a fully compromised server cert can't be turned into a CA, enforced cryptographically.
You know that moment when you're setting up a local dev environment and Chrome just refuses to load your own server, even though you know exactly what's running? You click Advanced, click Proceed Anyway, and wonder if there's a better way? The browser is right to warn you. A self-signed certificate is one where the issuer and subject are the same entity. No CA, the server signed its own certificate with its own private key. The handshake still completes. Key exchange still happens. The data is still encrypted. What failed isn't the encryption. Authentication. There's no trusted third party vouching for the certificate. Anyone can generate a self-signed certificate for any domain in 30 seconds with OpenSSL. So can someone who's intercepted your connection at a coffee shop router. The browser has no way to tell the difference because the CA, whose job is to make that distinction, isn't in the picture. The warning isn't saying the connection is unencrypted. It's saying the browser cannot verify who it's connected to. That's the specific failure. Use mkcert for local dev. It creates a CA on your machine, installs it into your system's trust store, and issues certs from it. Your browser trusts it because your trust store trusts it. Proper chain, no warnings, no clicking through. It takes 5 minutes to set up once.
Full picture. When you load https.bank.com, the handshake runs before any request goes out. The browser announces what it supports. The server sends its certificate.
The browser walks the chain, each signature verified up to a trusted root. Domain matches the SANs, cert is within validity. Authentication passes. Key exchange. Diffie-Hellman math that produces a shared secret without it ever crossing the wire. Session keys derive via HKDF. Symmetric encryption takes over. One round trip. Each piece does one job. The certificate proves identity. The CA's signature makes it trustworthy. The intermediate structure limits the damage if any single CA is compromised. Forward secrecy means a future key leak can't reach sessions from today. When something breaks, it's one specific link that didn't hold, and you know which one and how to check it. Before you close this, run one command on your own domain right now. That number is how many certificates your server is actually sending. If the answer is 1, just your server cert, no intermediate, mobile browsers and non-browser clients are probably getting a certificate error right now, and you don't know it. Next time a certificate error shows up, hopefully you know what can go wrong and where to look. The padlock was always just the surface. If you found this useful, please like and share. Thanks for watching, and see you in the next one.